Hello, everyone. Welcome to today's ACSL lesson. Today, we'll be doing some more practice on graph theory, which is a topic in contest number 4. Okay, to start, we are going to do some review from last week. So what is a graph? A graph is a nonlinear data structure that consists of nodes, which are also called vertices, and edges that join the vertices. So essentially, a graph is a collection of vertices and edges. An edge is simply a connection between any two vertices. And here we have two pictures of graphs. And let's do some quick review of some graph terminology, and then we'll get into a Kahoot. So a graph, which is commonly labeled with the letter G, is a set of vertices V and edges E. An undirected graph doesn't have direction, so that means edges can go both ways. Whereas in a directed graph, there is direction. So if we can go from A to B, that doesn't necessarily mean we can go from B back to A. The in degree of a vertex is the number of edges with V as the endpoint. So it's basically the number of edges that are coming into V, that are like pointing at V. And the out degree is the out degree of a vertex is the number of edges with with the vertex as the starting point. And a complete graph is a special kind of graph where we have an edge between every two vertices. And yeah, so I'll just skip over the rest of it now. We will see that in the problems later. So let's jump into the Kahoot. Can you all hear the sound? Waiting for more people to join. There should be 14 of you. Okay, I'll start. Okay, so most of you got this one right. A graph in graph theory is just a data structure that consists of nodes and edges. Well, it could be a chart showing data points, but not in the context of graph theory. Okay, how many edges does a complete graph with n nodes have? So remember, a complete graph like this, like the one in this diagram, has an edge between every two vertices. Okay, I think I forgot to change the time limit, but that's okay. So this is the same thing as n choose 2, because if we have n nodes and there is, since it's a complete graph, there is a edge between every two nodes, we are just choosing 2. Or you can also do, there's n possibilities for the first one and n minus 1 for the second one, and then we have to divide by 2 since we are double counting each of them. Okay. What is the minimum number of edges required for a connected graph with n nodes? So connected graph is just every vertex has a path to every other vertex, but not necessarily every two vertices have to have an edge. Okay, so the answer for this one is n minus 1. So let's say n is equal to 4 and we have four nodes. The minimum number would just be 3 edges for it to be a connected graph. So that would be n minus 1. Okay, R is in the lead. What is the degree of a node in a graph? So this is something Euler came up with. You remember from last week. Yeah, so it's the number of edges connected to the node. So remember in the famous bridges of Königsberg problem, Euler said that there has to be an even degree for every edge in order for the graph to be traversable. Oh, okay. So a cycle is a path that ends at the starting node. A cycle, okay, so the green option choice, a path that visits every node exactly once, would be the right answer for a simple path. And a cycle is a simple path, except that the first and last nodes are the same. So yellow would be a more accurate answer. So that was a quick review, and now we're going to get into some problems. Right, congratulations, Laura. Okay, let me close out of this. Okay, so this first question, we actually already did it last week, but just to review it, let's try this one. So find the number of different cycles contained in the directed graph with vertices A, B, C, D, E and edges A, B, B, A, B, C, C, D, D, C, D, B, D, E. So for this question, I would recommend drawing out the graph and then counting the number of cycles. Okay, so you can draw this pretty much however you want. So let's just say we have A, B, C, D, E. Oops. Um, and then we have the edges A, B, so that would be A to B, B, A, B, C, C, D, D, C, D, B, and D, E. Okay, so a cycle is a simple path that starts and ends at the same node. So A, B, A is one possible cycle. Okay, so how do we decide where the letters are put? It doesn't matter. What really matters is the connections. So the edges that actually matter. The actual position doesn't matter in graph theory. We are just dealing with the geometry of positions, basically. Yeah, so even if you draw it differently, you should still get the same answer. Okay, so ABA is one cycle, but if this were a undirected graph, it would not count because it has to have three or more nodes. But since it's a directed graph, these two paths are technically different, so that is okay. And then CDC is another cycle. And then we also have, let me use a different color. We also have BCDB. So this also counts as a cycle. So the answer should be 3 for this one. Wait, this pen is really weird. B, C, D, B. Okay, so the answer is 3. Yes, any questions? Um, okay, so what about A, B, C, D, B, A, B, C, D, B, A. So that would not work because you repeated B twice. So a cycle cannot repeat any nodes except the first and last one. Does that make sense? Yeah. Okay, so next question. Okay. A cycle always goes back to the original. Yes, it always goes back to the original node. Okay, so this for this problem, in the following directed graph, find the total number of different paths from A to C of length 2 or 4. And this loop thing basically means you can go back to yourself. Okay, so for this question, let's first consider only length 2. And we have to try to get from A to C. So the only one that works would be AAC. So we're taking advantage of the fact that A can go back to itself. And then for, so basically, for this question, I think we can sort of ignore B because you can, B is like disconnected from A and C. And yeah, you can't even go from C to B. So we can just completely ignore B. So now we can look at paths that are of length 4. So one simple case would be C. You just keep going back to A. And then for the last step, we can go from A to C. And then you can also mix up the combinations. For example, you can go from A to C and then go back to A and then stay on A and then go to C. That also works. And you can go from A back to A and then go to C and then back to A and then back to C. So these are the four possible paths. So the answer is four. Does anyone have any questions? Okay, if not, then we will move on. Okay, so for this one, how many edges must be added to the falling graph to make it a complete graph? So remember, a complete graph is a graph that has an edge between every two vertices. Oops. To make a complete graph, the degrees don't necessarily have to be even. That is if you're talking about a graph that is traversable, which means you can basically you can basically do a cycle to every node without repeating any paths. So if you recall from last week, yeah, the bridge of Königsberg problem, for that, for the graph to be traversable, it does need to be all even, but to make it a complete graph, we just have to have an edge between every two vertices. Yeah, so a complete graph is a graph where there is an edge between every two vertices. Okay. This problem is, yeah, relatively more simple. I see some correct answers. So um, basically, we just have to fill in any connections that are not there. So the most obvious one is AB, so we need to add that in. AD also, and EC. So the answer is three. Okay, so next question. Your job at the ACSL pizza shop is to deliver some pizzas to three different locations, a house, a school, and a motel. So how many different routes can be used to deliver the pizzas to all three locations? Okay, so for the first location, um we have three options, so three. And then for the second location, we have two options. And then for the third location, we have one option remaining. So this is the same thing as 3 factorial, which is 6. Um, Another way you could approach it is you can basically draw a graph, H for house, S for school, M for motel, and you can list out all the combinations. So HSM, HMS, SHM, SMH, and then MHS and MSH. So you will still have 6 different routes. So 6 is the answer. Okay, next question. In a rumor network, a message is passed from one person to another in many ways. If this graph represents a rumor network among 5 good friends, A, B, C, D, E, how many ways can Amy get a message to Evan using exactly 2 other friends? For this problem, the easiest way is to just list out the different paths, or you could use a matrix, but that is going to take too much time. So we have to use exactly 2 other friends. So we can do A, B, D, E. That counts as one. A, B, D, E. We can do A, C, D, E. We can also do A, C, B. And we also can do A, D, B, E. Oops. A, D, B, E. Yeah, so the answer should be 4 different ways. How many cycles of length 3 are in the following graph? Does anyone need more time? Okay, I'll give a hint. So a cycle of length 3 in an undirected graph has to have 3 different vertices, and they start and end at the same vertex. Okay, so for cycles of length 3, we have to have three different vertices. And so basically, we just have to find three vertices. You can also think of it as like a triangle. So one possible cycle is JKM. Another one is KLN. And another one is KJL. And there is one more. Let me see. And the last one is KMN. So there are four of these cycles, but cycles can go both ways. So we have to multiply it by 2. So the answer should be 8. Okay, can't you do KJL and KLJ? KJL. Yeah, so that is why um we have to multiply by 2. So it's the same thing as just counting how many triangles you see in this graph. But if ML were connected, which it isn't, then it would be a complete graph. And in that case, we can just do 5, choose 3 to find the number of triangles. But obviously that doesn't work. So we do have to manually count how many cycles there are and then double it. Okay. This problem, which edge could be added to make the following graph traversable from any vertex to any other vertex? A traversable graph is a graph where um, you can draw without taking your pen off the paper and without going over every edge twice. Yeah, so basically it's a graph where you can draw a path between all the vertices without retracing the same path. Okay, so just to clarify, the graph currently is already traversable. We can basically uh, um, go through every vertex without retracing any path. So this would be how you would do it. But how would we make it still traversable if we had to add one more edge. So it currently is already traversable, but if we wanted to add one more edge and still make it traversable, which edge would you add? Okay, so to do this problem, we have to first analyze the degrees of each node. So the degree is the number of edges that are connected to that node. So F has degree 4. um, because we have these 4 edges. G has degree 3. H has degree 2. J also has degree 2. And K has degree 3. So in order for this graph to be, this is annoying. In order for this graph to be traversable, then all of the nodes have to have an even degree. So we can see F, J, and H already have an even degree. So the question is essentially, how can we add one more edge to make K and G have an even degree? So the only way to do that, to increase each of these degrees by 1 with one edge, is to just connect them directly. But since there already is a connection from K to G, the answer is actually there is there is no answer. So there is no such a path that would work because G and K already have a path between them, so it can't be done. And this is a multiple choice question on the ACSL, and one of the answer choices was it can't be done, so you would have to pick that. It's a bit unusual. Okay. Next question. How many paths of length 3 are there in the following directed graph? Yeah, so a path is a sequence of vertices connected by edges. So for example, A, B, C, D is an example of a path. Wait, actually, that's not possible because this is C can't go to D. I'll give a better example. ABC is a path. But this is a path of length 2, so we're looking for the number of paths of length 3. And because this one is a directed graph and it's a bit more complicated, so this one does require the use of an adjacency matrix. Okay, so to do this problem, let's first construct an adjacency matrix for this graph. So from A to A, okay, so let's do A, B, C, D, A, B, C, D. From A to A, there is no connection. So along this whole diagonal, there's no connections because the node can't go to itself. From A to B, there is a connection, so let's put a 1 there. From A to C, there is a connection, and there is one for D as well. There is no connection from B to A. It's only one way. From B to C, we do have a connection. From B to D, we also do. From C to A, we have a connection. From C to B, we do not, since this is one way. Oops, what happened? Okay. From C to D, we don't have a connection either since it's one way. From D to A, we don't have a connection, it's one way. From D to B, we do have a connection, and from D to C, we do as well. So this is the adjacency matrix. And essentially, what we have to do is we have to raise this matrix to the third power to find all the paths of length 3. Okay, so I'm going to erase this part. Um, okay, my annotation thing is glitching. Let me see. Okay, so we just have to raise this entire thing to the third power. And okay, so let's do that. Okay, why can't I erase everything? Okay, so I'm going to redraw the matrix we just had. Okay, and let's first multiply this by itself. So this is going to be the square value, and then we have to cube it. So, okay, so going down like this, we have 0 times 0, 1 times 0, 1 times 1, 1 times 0. So out of the sum of all those products, we have 1. And then let's move on to the next column. Um, this is going to give us 1 as well. In the third column, 0 times 1, 1 times 1, 1 times 0, 1 times 1. So we have 2. And then for the last one, we have, let me color code it in case this is confusing. We have 0 times 1. And if you don't understand what's going on, I can write it out to show you. So we have 0 times 1 plus 1 times 1 plus plus what happened? Plus 1 times 0 plus 1 times 0. So if we add it up, this gives us 0 plus 1 plus 0 plus 0. So this is 1. So that this spot in the resulting matrix is 1. So I'm just showing the process, and it's going to take too much time to finish, and we're running out of time. So if we finish the product, we should get this. But this is the matrix squared. So we have to cube it. So now let's multiply this by the original matrix we had. 1, 0, 0, 0, 0. And then we will repeat the same process. We will go rows and columns and add up all the sums of the products. And the result of this matrix cubed should give us this. So basically what this tells us is, if I write the letters back so you can see visualize what's happening. Basically what this is saying is from A to A, so for A as the starting node and A as the ending node, there are 2 different paths of length 3. From A to B, we have two different paths of length 3. And from A to C, we have three different paths of length 3, and so on. So if we want to calculate the total number of paths of length 3 throughout this entire graph for any starting node and any ending node, we can simply add everything up. And the sum of that is going to give us 26. So the answer is 26. So this type of problem definitely takes more time on the ACSL, and with some more practice, you should be able to do it as well. Okay, so that is it for today's lesson. Thank you everyone for coming.
Bye. Thank you.
Bye, thank you.
Thanks, bye.
Bye. Thank you.